So, good morning. Welcome to Krishna's classroom. We continue with our discussions on orthogonal projections. And this time, having characterized orthogonal projections, now we look at some properties or some outcomes from this idea, which is important to develop the so-called spectral theorem. So we'll make a mention of it later. But now, right now, we assume the following: X is a vector space of dimension n, inner product space dimension over or even for so it's a finite dimensional vector space. Now let E and F be orthogonal projections on X, which simply means that you have these properties: E equal to E square equal to E star, and so also F square F star. So the first part, E equal to E square, assures that E is a projection, and E equal to E star along with that assures that E is an orthogonal projection, by which you mean the range of E is orthogonal to the null space of E. So also the range of F is orthogonal to the null space of. So range of E is orthogonal to null space of E, and range of F is orthogonal to null space of F. Now this is what we have by the statement that is, these are orthogonal projections. Now we define definition. Two orthogonal projections E and F are said to be mutually orthogonal or orthogonal to one another if zero or equivalently equal to 0. So this is the definition. What does this mean? says EF equal to 0, 0 linear transformation, if and only if X. So that means f of x belongs to the null space of, and therefore we should have what we have is this, that is range of is contained in the null space of E. So if you consider Fe also, okay, yeah. Okay, these two are orthogonal. That's the meaning of that. If Fe equal to 0 means range of E is contained in null space of F. So this is the meaning of that. Okay. Let us now look at or we will make a remark before that. E and F orthogonal, or let me write it as a theorem, I think, yes. Make the statement of a theorem. We will characterize the orthogonality, mutually orthogonal. If and only if range of E and range of is orthogonal to So E is a projection on RE, F is a projection on RF, and these are orthogonal projections. That means the complementary space that you use are RE perp and RF perp respectively. Okay. Now let us prove this theorem. So you assume equal to 0, EF equal to 0. So let X belongs to RE and Y belongs to RF. Then what we get is this. We compute the inner product of X with Y and show that this is equal to 0. Now this I can write as X is in RE, which means I can replace it by E X Y. And I can even write here Fy. Okay, therefore this is equal to X E star of Fy, which is equal to, now E equal to E star, which implies this is inner product of X with Fy. And X is in RE. Okay, right, EF is equal to 0, therefore this is equal to 0. Therefore now conversely, assume range of E is orthogonal to F. Then what you have is this range of E is of range of F you take as, yeah, then what we get is range of F is contained in perp. Okay. Equal to 0 for F, which implies EFX equal to 0 for because we are Ex equal to 0 means, see, you are RF is contained in Re per, okay, right. Now this implies EF x equal to 0 for every x. Since we have f of x belongs to range of A, which is contained in range of E. That's the answer. So that completes the proof of this. So EF equal to 0 if and only if you have Re is orthogonal to RF, right. So this result is useful for our later considerations. Now you see, you can look at some simple scenarios like you see, you have like in R3, you have a orthogonal projection. So which means, say, range of E is a plane through the origin, of course. Range of E. Now you see, you are talking about, this is the line orthogonal to, or the subspace orthogonal to this, which is Re per. Okay, so this is the resolution that you are talking about. So take any vector here, it is resolved into range of E and range of E per. That is the action of E. Now what about F? See, this says that E and F are said to be mutually orthogonal if Re is contained, is perpendicular to RF. Okay. If Re is perpendicular to RF in this case, means you see that Re perp has to be equal to RF in this case. I mean, it's a very simple scenario that you are taking. And more generally, suppose you are taking a, okay, let me generalize this. I mean, here at least you have a picture. Now let me talk about, take this as Re and this as Re perp. So this is Re and this is Re perp. Okay. So in that case, you see, you have a line passing through the origin as a subspace, which is the range of E, which means you are projecting always to that. And then what about F? So you take Re orthogonal to RF. So range of F. So F you take, see, RF is orthogonal to Re provided it is lying in this space. So this line is RF. Okay. So RF is orthogonal to RE, right? Then what do you get? Take a vector, apply E, then you are in RE, and then you see that you are taking that vector, the image of that, and then projecting it to F orthogonally. Then where do you reach? You reach 0. Okay. So that's the picture that you get. Okay. What about FE? You will be projecting to RF. You will be projecting to RF, and then if you go for the orthogonal projection, see, you will be going into some you will be applying E, and E will certainly carry this into 0. So you get EF equal to FE equal to 0. Now one example, another example is this. Let us take X which is an orthonormal basis. It's an n-dimensional orthonormal basis. Now we take M to be, okay, range of E to be span of xk, and range of F to be span of xn. Okay, with the further assumption that K is less than, you make this assumption, K is less than M. Therefore, E is a projection to the space spanned by x1, x2, etc. xk. F is a projection spanned by xm plus 1 plus etc. xn. Therefore, what happens to a general x belonging to can be written as, say, now apply, if you apply, okay, so you apply F. If you apply F of x is going to be what? F of and this turns out to be something like Cm plus 1 xm plus 1 xm, because you see that f of x I equal to 0 in the when I ranges from 1 to m. and otherwise it is itself. That's the action that you have. Therefore, now you take E of f of x will be apply E on that. Then you see that these vectors do get mapped to 0, therefore you get 0. Okay. On the other hand, let us work with Fe. So E of x now you write f of E of x. This you see that E of x, f of x1 is 0, etc., f of xk equal to 0. Therefore, and this is equal to 0. So, EF equal to 0, FE equal to 0. So, this is a more general scenario that you have. Okay. So, we shall need this result later. So, let us work on this now, this application. One of the important applications that you come across is the situation where you see that or it's a sort of preparation for writing down the spectral theorem later for certain class of linear operators on inner product spaces. We will see later, but we will just prepare the ingredient now at the moment. Suppose E1, E2, etc., En are orthogonal projections, okay, or E1, E2, etc., En are orthogonal projections. Make the following. Of course, this n need not be the dimension of x. Now, let us take the dimension of x as some number which is not, or I can write it this way. Right. Bracket orthogonal. Okay. Then a necessary and sufficient condition that E equal to you know that sum of the linear operators is again a linear operator. So, you are asking whether it's an orthogonal projection. That's a natural question that you would like to ask. Be a perpendicular projection I think I should write here projection. Perpendicular projections is that EI that means EI and EJ are mutually orthogonal for all values of I and J. Okay. So the question that you are asking here is, when is the sum of orthogonal projections an orthogonal projection? Okay. So let us prove this theorem. This is quite simple to prove. So we start with sufficiency. Assume equal to 0 for 1 then what you have is, what we want to show is that E is an orthogonal projection. That is, E defined by E1, E2, etc., Ek is an orthogonal projection. So what do we do for this? We make use of the first characterization, namely that E is a projection, by showing that E is equal to E square, and then showing that it's an orthogonal projection by observing or proving E equal to E star. Okay. So E square, so let us compute. E square equal to, this assumption is that this is our basic assumption. E square equal to because all the Ei, Ej terms will go to 0, it will become 0 because of the assumption that Ei, Ej equal to 0. And this, you know, these are all projections, E1, E2, etc., Ek are orthogonal projections, which implies that E1 square equal to E1, which is equal to E, which implies now it is sufficient to prove that E star is equal to E. So now it is sufficient to prove that E star. You can easily work this out. So what is E star? So my claim is that E star is equal to sigma Ei star. Okay, so let us work on this. So if you have Ex y, this is equal to sigma of I have taken sigma inside and then taken it out, and you see that this is equal to sigma inner product of x with Ei star y k, and that is essentially inner product of x with sigma and what is that? EI star equal to EI. Since EI star equal to EI, that's equal to and this is true for every x, y belonging to x. What does this mean? Therefore, it is not only a projection, but it's also an orthogonal projection. Now we prove the necessity part. So we have proved the sufficiency part. Now we prove the necessity part. Necessity. Assume so this condition is satisfied. That's what we work with. Okay, so what we have, suppose you take an x belonging to range of ei for some I lying between 1 and k. Then we have norm of x whole square is greater than or equal to this is a consequence of the fact that our assumption that E is an orthogonal projection. We are using the second characterization. This is true for every x and in particular for x belonging to range of EI. And this is equal to and if you expand this, then you see that this is equal to sigma so that becomes and that's equal to that is Ejx x is, see I can write there Ej square x etc. and then I can use the orthogonality of the projection Ej and from that I get this result. And this of course is greater than or equal to because it is one of the components of this whole thing, and this of course is what you start with. We have started with EIX is x, therefore this. So what is the implication? That is norm x square, there are string of inequalities. So these inequalities are squeezed between norm of x square and norm of x square for x belonging to Ej. The consequence is that Ej x equal to 0, j not equal to I. Otherwise this is not going to be true. That is, x belongs to, okay, range of EI. EI null space of Ej for j not equal to I, which implies now you see it's true for every I, therefore this result is true. So that completes the proof of the theorem. Well, if you want, you can write this is true for I 1 okay, so that completes the proof of the theorem. So a necessary and sufficient condition for E to be an orthogonal projection, where E is the sum of E1, E2, etc. of the sum of the operators orthogonal projections E1, E2, etc. Then what you get is this, is that EI, Ej equal to 0 whenever I is different from j. Of course, I think I should write that also. So we now look at some more properties which are a sort of kind of order relation that you have. Okay. So we ask the following question. Suppose, so given projections on range of E and we ask the following question. what is the question that you ask? We ask, when is it E less than or equal to F? What does this mean? This means F minus E, F minus E is positive definite. Okay, so that's the criteria that we have. So let us start with this. So that is or at least semi-positive definite. So let us have the following theorem. We will give a characterization of this concept, which we shall need some time or other. Theorem. F. The following conditions are equivalent. The first condition is, the meaning of this is that F minus E, the linear transformation F minus E is semi-positive definite, by which you mean this property. We'll give details of that soon. This is equivalent to saying that norm of Ex is less than or equal to norm of X. Then the third condition, an equivalent condition, is that range of E is contained in range of F. The fourth condition, fourth A, is condition that Fe equal to E, and fourth B is that EF equal to E. That means they commute. So these are the equivalent criteria for this. Now let us prove this here. The first part is so we prove 1 implies 2. We prove it cyclically, that we prove 1 implies 2, 2 implies 3, 3 implies 4a, 4a implies 4b, and then 4b implies 1. So that's how we prove this. Okay. So what is assumption? Assume E is less than or equal to F. Then what we have? Then for every x belonging to x. This is what you get. 0 is less than or equal to the inner product of f minus e x, and this is equal to inner product of fx minus inner product of exx. This is true for every x. Now, what does this mean? See, this is f square. This is f is equal to f square. So, you can write this as which is equal to f, but f is equal to f star being orthogonal. Therefore, this is equal to whole square. So, what does that mean? This implies norm of Ex so that completes the proof of the first statement that 1 implies 2. The next step is assume 2 and then prove 3. Assume 2. This is the next step. So assume norm of Ex now you start with, so what we claim is this. So we start with a x array. Then what we have is this norm of x is greater than or equal to norm of fx, and we have to use this, and this is certainly greater than or equal to norm of Ex, and norm of Ex is equal to norm of x because x is in the range of E. Okay, so what does this mean? This implies equality holds here in between. Okay, this implies range of. That's what you have to prove. So that's complete now. It's quite easy to prove, and if you want, you can use this the explanation. Equal to 0. This implies zero, or this is equal to so that's the proof of this. Okay, so here you have used that I minus f is a orthogonal projection. So this step to this step, we have used that I minus f is an orthogonal projection. Okay, it's quite easy to prove. I minus f square you take, and you can show that it's a projection. And then you also show that see, you have f star is equal to f, and use that to prove I minus f star equal to I minus f. Okay. Now we prove for A. So what is this? You have got range of, assume then claim so range of E implies Ex belongs to that's the implication, and that implies which implies Fe sorry, this is Ex, therefore Fe equal to E. So Fex is equal to Ex for every x belonging to X, and this implies Fe is equal to E. So now we prove the next statement, next implication, namely 4A implies 4B. Okay. So assume equal to E. Now Fe equal to E implies Fe star E, which in turn implies E star F star is equal to E. But E star is equal to, being orthogonal projections, E star is equal to E, F star equal to E. Now since so that completes the proof of that. Now there is only one more thing to remaining, that is, if you can prove 4B implies 1, then the cycle is complete. So we prove that. So that completes the proof of the theorem. Now let me start here. Assume EF equal to then, so what is the claim? So that cycle will be complete. So if for every x E implies for every x, this is what you get, fx x minus exx, this is equal to f of x. Since E and F are commutative, projections, so also E and F and I minus E, they commute each other. Okay, so let G be G define I minus F into I minus E. Then what do you get? It's a projection, and therefore this is equal to, we have Gx, and this is norm of whole square, and this is greater than or equal to 0. Okay, which implies F is that completes the proof. So these equivalent forms of the same result often helps you to pick the right one required for application at some place whenever one of these conditions are assumed, all others would follow. So that's the whole purpose of this kind of results. So they are equivalent forms of the same statement. And with this, I think we stop today's discussion. Thank you very much.